So first, I would like to give an introduction to PM2.5 and satellite AOD. PM2.5 is one particulate matter with diameter smaller than 2.5 micrometer. It is so small that when you breathe, you can take it into your respiratory system and deep into your lung and maybe penetrate into your blood. So it have human effects on a health effect on human beings, and that's why we care about it. A reliable to get estimation of the PM2.5 in your location is to get the PM2.5 concentration from the nearest PM2.5 monitors. However, even the distribution of the PM2.5 monitors has spatial biases. You can take a look at this figure at the top right corner. This is a figure published on atmospheric environment in 2019 from Randall Martin. And in this figure, you can see that in North America and Europe, the PM2.5 monitors per million person can reach maybe 3, 4, maybe even larger than 10. But in East Asia, in China, Japan, in South Korea, that is only maybe 1 to 2. And in India, it's more than 0.2. And in Africa, they may, in the whole country, they may have no PM2.5 monitors. So the distribution of the PM2.5 monitors gives us a difficult to get the estimation of the global PM2.5. So we have to rely on other tools to estimate the surface PM2.5. And one way is to get the satellite graphs of aerosol optical depths, the AOD. It has continuous spatial coverage and long-term series data size. But the aerosol optical depth is a column variables. It contains information in the vertical direction, and it has a nonlinear and complicated relationship between the surface PM2.5. So to get an estimation of the surface PM2.5, when you rely on other tools. And one is the CTM model simulation. Here we use geophysical. It has rich data, complete spatial temporal coverage, and has many compositions. So with the help with the satellite AOD CTM simulation, Erwan Deckler first proposed this the geophysical PM2.5 in 2006. Geophysical PM2.5 equals eta multiply the satellite retrieved AOD, and eta is PM2.5 from model divided by AOD from the model. So we use the model to find the eta, and then we can apply the eta to the AOD, and we get the global PM2.5 concentration estimation. But the uncertainty in geophysical PM2.5 need to be studied because the model is not perfect, the AOD data set is not perfect, and AOD, satellite AOD usually has a finer resolution than the CTM model. So when you regrade the situation, you may also bring some biases to the PM2.5. So this uncertainty need to be studied. Previously, we have already applied some way to improve the geophysical PM2.5. Erwan Deckler used the geographically weighted regression method to improve the geophysical PM2.5. GWR is you can take it like a multiple variables regression, add some geographic weights that you can see that with GWR he have already reached some good results. And this paper published in ESNT in 2021 is kind of like a benchmark in this project. So, however, even though he got some very good result estimation of the surface PM2.5, but GWR is a very simple method. So based on the data sets that we have, we are thinking that how about we use deep learning to get another model to estimate the global PM2.5 that may be better than the traditional ways that we did in the past. So in this project, we choose to use the convolutional neural network. Here is a brief introduction to convolutional neural network. A CNN is a neural network with some convolutional layers and some other layers. The convolutional layers has a number of filters that does convolutional operation. A convolution operation in this scenario is a dot product of two flattened matrices. Here is an example. If you have input that has 6 by 6 grids and you select a 3 by 3 image patch here and you apply a 3 by 3 kernel on it, then you have output. This is 31. Like if you apply this kernel on this image patch, you have 1 plus 3 plus 5 plus 6 plus 7 plus 9 and equals 61. And then the output, you have a 44 by 4 images. So how a kernel works, here is the image on the left shows the dimensions of input and kernels. The input usually have 3 dimensions. It has heads, right, the side, the first 2 dimensions describe the size of the images, and the third one is the channels or the features. In computational vision, they use like RGB, but in our community, we usually use like material fields, emissions, LD. And for the kernels, it has 4 dimensions. The first 2 is the size of the dimension, size of the kernel, and third one is input number of input channel, and the fourth one is output of number of output channel. So the features, number of features can change during the convolution process. And on the right, you can see how kernel move our input image and have output images. You may notice that this dashed grids here, this dashed grids, we call it padding grids, that if you have padding grids, you can remain the size of images during the whole process. So what can convolution layer do? Convolutional neural networks are usually used for visual imagery, helping the computer identify and learn from images. To give the computer vision to help it stay an input image, classify it, see patterns, and overall learn from it. Here is an example shows how the computer detects edges with a filter. So as human beings, we can easily see that this is dog and this may be snow, and we can see this. This is years, something like this. But how the computer knows? We apply a very simple filter. It has 2 numbers, +1 and -1. When we apply this filter on this input model, if 2 neighboring grids that they have similar values, then the output should be 0. If they have 2 values that has big difference, which may indicate that this is the edge of an object. So the output should have an absolute value that is much larger than 0. So the convolution layer can capture the spatial correlation in an image, and meteorology fields emissions LD can also be taken as figures, and we believe that PM2.5 has spatial correlation with the surrounding grids. So we think that the convolutional neural network may help us to improve the geophysical PM2.5 estimation. And this figure shows a hole there. You have an input and you put it into the convolution layer, exporting batch normal layers and activate function. And this can repeat many times, and then you flatten it and put it into a fully connected feed-forward network. And you can choose the output either classification that you have many bins, you put this PM2.5 as maybe in this bin, and then you average have an output, or you can choose to run a regression task that to output the PM2.5 value directly. There is a workflow of this project. This is data source downloading, processing. And one thing you may need to notice is that the label data in this project is the geophysical bias of geophysical PM2.5. The geophysical PM2.5 bias is equals to ground truth minus geophysical PM2.5. And this is also our direct output from our model. And then we plus it with the corresponding geophysical PM2.5 and to do the validation and to the hyperparameters and have the validated the model, and then we have improved global PM2.5 estimation. And this is the location of the ground truth size and validation areas, which we validate the model in 4 areas: global range, North America, Europe, and Asia area. And this figure shows at the bottom shows the ground observation PM2.5 distribution from 2015 to 2019. We can see that the global North America and Europe, they all have a peaks, maybe around 10, but the Asia area, it has a long tail instead of have an obvious peak. The total number of ground sets is like over 10,000, and North America is 2,800. Europe is around 3,000, and Asia is around 3,500. And since we are doing a regression task, initially we trained the model with the MSE loss function, which I showed here. So this table shows the spatial cross-validation results with comparing with the model trained with MSE loss and benchmark the hybrid PM2.5 from Aaron Decker. This table have four colors, and each color represents different areas. Orange global, green is Asia, blue North America, and gray is Europe. And each color has two columns. The left column is a convolution roof is the Siyuan with MSE, and the right column is the benchmark. And the color, the digits have red color, means it performs better in two algorithm, and black means it is worse. So we can see in global range, Asia and Europe, the Siyuan performs better than the hybrid PM2.5. But in North American area, they are comparable, and in April it's even worse. So this leads to me that of thinking why the global model performs bad on North America, and how can we solve it? So here is the distribution of the PM2.5 bias in Asia and North America. The left is Asia and right is North America. We can see that Asia has longer tails than North America. And the bias of Asia can reach -100 to positive 100 microgram per kilometer, but North America is only maybe 10, 15, -15 to positive 15. So when we use MS loss function, that you may have small the North American parts can contribute a small portion of the loss to the total loss. So the model may find, when the model do the gradient descent, it may find out that the Asia, if it cares more about Asia, then the total loss can decrease a lot. But even though it ignores the North America area, so to change the way we train the model, we need to increase the weights of the loss from the low bias area. So we use an adjusted loss function that we put coefficients before on the MSE loss. And this is 1 plus beta multiplied e to the minus alpha y square, and the beta chain controls the largest value of the coefficient, and alpha changes the shape of this coefficient that you can decide, in what range that you want the adjusted loss MSE loss function have effects on. So this table shows the performance of the model trained with adjusted MSE loss function, and also 4 areas. And the left column shows the Siyuan with adjusted MSE loss. The middle is normal MSE, and the right one is a benchmark. And the number with red color means the best, pink is the medium, and the black is the worst. So we can see that even though we sacrifice a little bit performance in the global range in April and July, only a little bit, but we in North American area, the model trained with adjusted MSE loss function, that it does better job than the normal MSE loss function and the hybrid PM2.5. And we also increase a little bit in Asia, July, and Europe, April. So with the adjusted MSE loss function, we make the model to improve let the model improve the performance on North American without hurting the performance in other areas. So I think this is great. However, we still have remaining questions there are nodes in the PM2.5 map from model trained with adjusted MSE loss function. You can see that in Tibet, this is the PM2.5 map over China in January 2018 and July 2018. You can see that there are some nodes over the Tibet areas and Mongolia. And Tibet is no one lives there, and the emission is very slow, and this has high elevation. Shouldn't have this high PM2.5. In this map, it reaches about 80 microgram per cubic meter, but previous public papers or the range size data that shows that it should only have smaller than 20 microgram per cubic meter. So how can we? So I'm thinking to solve this problem by adjusting the loss function. Here is the figure shows distribution of bias ratio to geophysical PM2.5. The bias ratio to geophysical PM2.5 is just the bias divided by the geophysical PM2.5, divided by the corresponding geophysical PM2.5. And we can see in global range, most of the bias ratio is within the minus 100% to 300% this range. So we are thinking that how about we give the model of penalties, then it performs a bias smaller than minus 100% geophysical PM2.5 or larger than 300% geophysical PM2.5. So here I design a MSE loss function with penalty terms. We use the ReLU function here. The ReLU function is like you give a x in it, and if it's smaller than 0, output 0. If it's larger than 0, output x. So in this adjusted MSE loss function with penalty terms has two penalty terms. First one is like the first penalty term will give a penalty to the cost function when the bias output is smaller than minus 100 geophysical PM2.5. So this is very obvious because we do not want the model to output the bias smaller than minus 100% geophysical PM2.5. Then in that case, you may get a minus PM2.5. This is ridiculous. And the second penalty term will give a penalty to the cost function when the bias output is larger than gamma geophysical PM2.5. And gamma can be maybe 2 or 3. It depends on what range you want to give a penalty terms. And lambda 1 and lambda 2 decides how strict this regularization is. If you have large lambda, then it's very hard. Then it's a very hard regularization. If the lambda is small, then you have a soft regularization. So when we apply the penalty terms on the cost function, this is a penalty terms with gamma equals 3.0, and we can see that the nodes over Tibet disappear, and the PM2.5 is around maybe 10, smaller than 10, and this is good. And how the penalty terms hurts the performance of the model. And here, this table shows the performance of the adjusted MSE loss function with penalty terms. So you can see that the first column is the adjusted MSE loss function, and the second column is adjusted MSE loss function with penalty terms, and third is the benchmark. We can see that in global range, it does not have a hurt on the performance. It hurts a little bit in Asia in January and April, and in North America, it hurts a little bit in annual and January. January it hurts a lot. I don't know what the reason this is. I can say it's abnormal. I don't know what happened. And in Europe, surprisingly, it increased the R-square. It helps the model to improve the performance. This is very surprising. And so I think this result is acceptable because we only have some here. I don't know. This is, I think this is a really interesting result because it's only effect on the January in North America. So I'm glad to figure out what's happening here in the future. And here is a robust test. I would just run to do this robust test. I just want to know because because North America and Europe and East Asia, they already have a lot of observation sites, but in Africa and South American, they have very little number of observation sites. So I withheld 99% of the data sets as the testing data sets, only 1% as the training data sets, and 95% withheld, 90% withheld, and 80% withheld, and 6-7% withheld. And this is the normal turn-fold cross-validation. And we can say that even though we have only 100 sets to train, that in the global range, the R-squared can reach 0.73, and Asia and Europe can reach over 0.4. So which may indicate that the robustness of our model is very high, that even though we apply the model into a area-based sparse size distribution, we can still get reasonable results. We can still we can believe, we can trust the results from this model. So here is a brief summary. It's like, first is the convolutional neural networks performs better than traditional statistical method, hybrid algebra in estimating PM2.5 with the same input data variables. The second is by adjusting the loss functions, the performance of the model can be improved to achieve our goal. And through the robust test, we found that our model can still maintain a relatively good performance in global and relatively high concentration areas, and the distribution of the observation sites is sparse. Okay, that's all for my presentation, and thank you for listening. If you have any question, please ask.
This is a great talk. I was wondering if you could talk a little bit more about how you fixed your problem in areas without very many observations, because I remember you talked about this pretty recently, about that being a problem, and I just wanted you to point out, in more detail what it is that you did to solve that.
Yeah, just like so just like I mentioned here.
Yeah.
There are some nodes in the Tibet, right? So I'm thinking that this shows the distribution of the bias ratio, which means this is bias. The bias is the ground truth minus the geophysical PM2.5, and the ratio is the bias divided by the geophysical bias divided by the corresponding geophysical PM2.5. And we can say in the global range, it's within from minus 100% to 300%. So we think this is a reasonable. So we think that for the bias, it has a reasonable range, that it cannot be maybe too large. So if we add some penalties to the model, that it tells the model that if you give a bias that is ridiculous, is very high, it's much higher than geophysical PM2.5, then you are doing something wrong. So that's how here we put some penalty terms here. Let's say for the first penalty terms, if you have this this fxi is the output from the model. If the fxi is smaller than minus 100% corresponding geophysical PM2.5, this value here we will give a positive. So it may increase the loss. And here in second term, if you have a bias output larger than gamma, multiply geophysical PM2.5, then it will also give a positive loss to the total loss, and which means that it gives a penalty. So with these two penalty terms, we can constrain the model to, we can constrain the bias to a reasonable range. Do not need to worry that it may hurt the model in estimation very high or extreme values, because even if you have extreme values in the geophysical PM2.5, the a priori value may also be very high. So and then the range is much larger, because this is just depends on the ratio, not on the. It's kind of like a ratio penalty, not a absolute penalty here. Yeah. So in this case, we can solve this problem like in Tibet with no observation set area.
This is a really nice solution. Yeah, I might bug you about this a little bit. When I'm trying to fix my own thing, so I might pick your brain at some point. Yeah, this is really
Yeah, sure.
Drew, did you fit directly to PM2.5 as opposed to this bias? Or
I did fit directly to
Okay.
PM2.5, so that limits my ability to use a CNN the way that Siyuan does. Although there is someone who has figured out how to do CNNs trained on missing data that I've chatted with, which involves some pretty clever little disconnecting nodes. But yeah, it's a different method, for sure.
Yeah, I've got a methodsy question. Could you go back to the cost function?
Yeah, sure. Which one? This one?
So yeah, well, so the first one I haven't seen this. Did you come up with that one?
Yes, last time the Redshift referred a published paper on it that it has an exponent. It gives an example of only have this factor like this, and then I'm thinking this may help. So it inspires me, and then I designed this coefficient here.
Yeah, and then you incorporated kind of these constraints, trying to constrain the bias space. Did you find that so this is like, a soft constraint because it's in the cost function. Did you find that you had some cases that still exceeded it?
I didn't check, actually. I didn't check point by point, but I believe because the lambda here is very small, as said, is maybe only 0.1 or 0.2, so it's very small. My batch size is 500, so and the loss usually is maybe 100, so 0.1 I think is a very soft constraint here. Yeah.
Yeah. Okay. Well, I'd be curious if it's, just if you have things that are going against the terms of the cost
I may check in the future. Yeah, it's just a very good question. Yeah.
Yeah. And one last question. Am I right to interpret that first adjusted MSE loss function without the additional regularization? Is that just like the higher the bias is, the less it gets weighted? Is that like a
which one? This one?
Yes. Yeah. Is that
if the bias is very small, if the bias is slow, then it give a higher coefficient. It means that you care much more on this area.
Yeah, cool.
Yeah.
Makes sense. Thanks.
All right, I have a few questions. So I'm surprised this cost function, loss function works so well. It fixes a lot of your problems. Have you tried to make separate neural nets for like different continents? So like a North America specific one, an Asia specific one, and how does that compare to the global?
Yeah, at the beginning I did that, but Ron Martin told me that well, we do not want that. Yeah, we want the global map. Well, we want the global model. So if I use the area models, I do not need this function here. I do not need the adjusted MSE loss function. Yeah, in that case, the initial MSE loss function is enough that the North American model can perform better than the benchmark. Yeah.
And do you show PM over like the oceans, like African outflow? Do you see that, or is that kind of ignored with because you zero out the ocean?
We do not estimate the PM5 over the ocean because we do not have observation size over ocean, and no one lives here, so we do not care about. Yeah.
Okay, and another question is, the geophysical PM2.5 is based on like a model, so GeoSchem, and that's specific to a version, and the AOD and PM always changes in GeoSchem. Does that mean you have to retrain this model for like version 14 point yada yada?
I don't think so, actually. Yeah, I think because our input variables has a lot of variables from the GeoSchem. I mean, even if the different version may have a little bit difference, I don't think it can bring a big difference in this model. Yeah. Even though if we have different variables and we retrain the model, it may only take 1 hour. Yeah, because training a model is very quick. Yeah.
Okay, and sorry, one last question. Can you go back to your the final distribution of your bias outputs that you show? Yeah. So I thought it was interesting
this is
because
not output. This is not output. This is the ground truth versus
ratio to geophysical. So
this is just to show that why I put handy terms here.
So bias, what is this? Distribution ratio, bias ratio to geophysical PM.
Yeah, this is the geophysical. This is the ground truth minus geophysical PM5 divided by geophysical PM5.
Oh, okay. So this is not related to your trained model at all.
Yeah, this is not. This is just to show why we can apply these penalty terms here, because statistically, the bias is within a ratio of the geophysical PM5. And so make sure that this penalty term makes sense.
Yeah, and so I guess my last question would be, I'm curious if you did some other metric instead of R squared, like RMSE, because this distribution ratio you show is pretty interesting because it's like the bulk of the these biases are negative, but it has a really long positive tail. And so, I mean, you show that you aggregate to like monthly PM. Is this something that you can predict in GeoScam at like a daily level, or is it aggregated to the month and all of that is done there? Or because I'm curious how like it's difficult to predict the really extreme PM events, and this also shows like a generally negative bias. So yeah, just curious.
So could you please repeat your question?
So it's like how
at the point.
So can this be done, like, is your model for every single day, whatever output, or is this for monthly averages? And can you capture like the highest extreme events in like Beijing in the winter?
Yeah, just because this just I mentioned before that you do not need to worry, because if you have an extreme things that the geophysical PM5 is base of the geophysical can be very high. So if you apply because this is gamma is like a ratio. If you have a high base of geophysical PM5, then you can have a higher base value in this area. Then you can still get extreme values in this area. But this depends on the performance of the model and the LD. If the geophysical PM5 in that area maybe the very low quality, maybe there should have a wildfire and we didn't detect, then the model cannot give the true value, I think. Because actually because the many like AOD and eta is also input variables in the model. If the geophysical PM5 is wrong at that point, that means the input variables, the input data are already wrong. So the model cannot capture that extreme value that I think it's normal. Yeah, but if the geophysical PM5 value makes sense in that area, then the model can indeed it can capture the extreme values. Yeah, even though we apply these penalty terms here. Does this answer your question?
Yes, thank you.
Can I ask a quick question since we have 3 minutes left? In your CNN configuration, and each observation will be an image and image of every input feature, right? And yeah, for this image, is that a global map or you select a curtain range?
No. I use 11 by 11 images.
How do you determine? Yeah. How do you decide 11 by 11?
it's kind of like a trade-off between the performance and the time you train the model. When you so I tried from 3x3 until 21x21. I found out that 11 has better performance, nearly the best performance, and it doesn't take a much longer time as the 21 does. So I decided this one. I mean, this is kind of like you do a lot of tests and choose the best one. Yeah.
Yeah, I just want to relate it to my OH project because OH is so short-lived. So it probably doesn't make sense to have the image as a training because it's only the OH is only determined by the chemical species at the same
depends
grade.
on the lifetime and the time resolution, the temporal resolution you have in your project.
Yeah.
Yeah.
Thank you.
All right. Thank you, everyone. I'm going to go ahead and stop the recording.